I want to take a quick second to talk about the what a mole is, or how do we actually communicate the number of particles that we have in a solution, like the number of molecules or the number of ions that we have. And there's in any given solution that's filled with like different atoms and molecules, there's just so many. We're talking about really large numbers of molecules in what feels to us like a small or normal size space. And so we talk about atoms and really tiny things in terms of the number of moles of them we have. And the mole is one of our counting numbers. It is similar to a dozen or a gross or I guess those are the only two that I know off the top of my head. There are other ones. But so this idea of a number of things is similar to like 1 dozen equals 12 things. And when we think of a dozen, we often think about a dozen eggs or a dozen donuts or something like that. 1 gross equals, I think, 122 things. Double check that. 1 gross is 144 things. And for some reason, the only thing I can think of are bouncy balls. Like that's the only thing I think I've bought a gross of in my life. But I've bought a gross of bouncy balls. I've bought several gross of bouncy balls. And so if we're going to talk about molecules, we're going to, instead of talking about them in dozens or grosses or the number that they are, we'll talk about them in terms of moles. And this means at the end of the day, you get to use less scientific notation. So that's the benefit. So a mole can be anything. It can be atoms, it can be molecules, those are the most common, but it could be donuts, it could be bouncy balls. So it's going to always be this number right here, 6.02 times 10 to the 23rd. That is just huge, right? It's a lot of zeros, and that's me rounding just to 3 sig figs. It's a lot of zeros. So when we use it in calculations, we're going to use it to say we have a certain number of things, but we're not going to individually count out atoms or molecules. Like that's insane. So instead, we're going to actually count out things by mass. This is what you would do if you made lots of bouncy balls. You would sell them to someone either by mass or they would weigh what a gross is, say like, oh, it's 3.7 pounds. So if I need to buy 2 gross, you would just weigh out 2 batches of 3.7 pounds of bouncy balls and give them to me instead of counting out the 288 bouncy balls I ordered. It's just much faster. We do the same thing with atoms and molecules. And so here's the thing, at 1 mole of carbon right here, if I just take a mole of carbon atoms and I weigh it, it's going to equal 12 grams. And this will be different for every different element, right? So oxygen, if I weigh 1 mole of oxygen, it'll weigh 15.999 grams. If I weigh 1 mole of hydrogen atoms, it'll weigh 1.08 grams, 0.008 grams. And so each element will have a different mass because they have different numbers of protons and different numbers of neutrons. And so we can weigh a pure substance and then know how many atoms we have because we can relate the number to a mass. And so this is what we call the molecular mass or the molecular weight. And these numbers, it's the same thing on Earth, right? Because mass and weight will be the same numeric value given our gravity. So the molecular mass mm or molecular weight mw, which we will use interchangeably, is really equating the mole, the number of moles of something to mass. So we can weigh out a substance instead of counting out atoms. And so going back to our carbon example, if 1 mole of carbon atoms weighs 12 grams, this starts to look a lot like a conversion factor. It's like an equality. So we can actually also write it as a fraction, 12 grams per mole, as in 12 grams is the weight of 1 mole of carbon atoms. So we can calculate this molar mass for any compound using the periodic table. So when you look at the periodic table for carbon, And they're all a little different, but they'll have the big element symbol C. It'll also have the atomic number like 6. That's the number of protons that it has. And then it'll usually have a number that has a decimal place after it with some like decimal-y numbers, unless they get really big and then they're all whole numbers. This right here is our molar mass or our molecular weight. And remember, this was also our atomic mass, which we used units of AMU, and molecular mass and molecular weight will use units of grams per mole, and it's the same numeric value. The conversion factor between AMU and grams per mole is gnarly, and we won't do it here. It's not equivalent. They're not exactly the same. It's just a nice, easy little coincidence. We have a very funky conversion factor that gets us between the two and allows that numeric value to be the same. So if I wanted to know what the molecular mass of CO2 is, I would take the molar mass of carbon and I would add it to 2 times the molar mass of oxygen. So it would be 12.01 plus 2 times 15.999 grams per mole. I'll put grams per mole over here too. That 2 is coming from this mole ratio that's within our chemical formula right here. So this chemical formula is stating I have 1 carbon atom and 2 oxygen atoms. So if I add that up, I'm going to end up with 44.01 grams per mole. And that'll be the molecular mass that I have for my carbon dioxide. And I can use that then to take a mass of something and convert it into a number, the counting number in moles. So if I have 1.0 gram of CO2, I can tell you how many CO2 molecules I actually have. And I can do that by multiplying this. So I have grams on the bottom. So our grams will cancel out, going back to dimensional analysis, and moles on the top. So it's going to be 44.01 grams for every 1 mole of carbon dioxide. And so I'm just going to be dividing that 1 gram of CO2 by 44.01 in my calculator. And I get 0.0227 moles of CO2. So now I have a counting number associated with my molecules of carbon dioxide rather than a mass. And then I can use that to calculate a concentration. So let's say I'm looking at how much CO2 is actually dissolved in some amount of water. So if I have 1.0 grams of CO2, that'll equal 0.0227 moles of CO2. Let's assume this all dissolves in, gosh, I don't know what it would be. Let's call it 100 liters, right? 100.0 liters of solution. And we'll just say it forms a total volume. So I can calculate molarity then. Will be the moles of CO2 divided by the volume of the solution in liters. So that's going to be 0.0227 moles divided by 100.0 liters. And with molarity, it's important that that volume is in liters. And then that'll equal, divided by 0.000227 molarity, or moles per liter. So hopefully that helps with this moles piece. We'll work on it more when we talk about chemical reactions and stoichiometry soon.